You think black holes only exist in the far reaches of deep space? In 2008, in the underground of Geneva, Switzerland, a group of scientists pressed the start button. The machine they activated was calculated to have a probability of creating a black hole on Earth. What does that actually mean? A black hole's gravity is so strong that even light cannot escape. Once formed, everything on Earth, your phone, your house, every person you've ever seen, would be ruthlessly compressed into a point the size of a needle. Then, we'd be erased from the universe entirely. But here's the strange part. It's been 18 years. We are still alive. You're still holding your phone, watching this video. So, were those scientists crazy? Or did they know something we didn't? Even more chilling, CERN's official website states in plain English that their machine, the Large Hadron Collider, could still potentially produce black holes today. Why aren't physicists stopping them? Why isn't anyone saying this is too dangerous? Are we all playing a game of Russian roulette where we've just been lucky the chamber was empty? Today, we are going to peel back the layers of this global panic. We'll look at what this 27-kilometer giant is actually doing underground. Is it really going to create a black hole that swallows the Earth? First, let's look at this machine, the Large Hadron Collider, or LHC. It is the pinnacle of human engineering. Imagine a 27-kilometer circular tunnel. It is packed with 9,593 massive magnets. Their job? To accelerate protons and heavy ions to 99,999,999, 1% the speed of light. Then, they smash them head-on. How fast is that? In the time it takes you to blink, these particles have circled that 27-kilometer ring several times. The machine generates 1 billion collisions every second. It consumes 600 gigawatt hours of electricity per year. That is enough to power a city of 100,000 people for an entire year. But why spend all this money? Simply put, they want to recreate the extreme conditions that existed fractions of a second after the Big Bang, just on a microscopic scale. The physics here is fascinating. When those accelerated particles collide, their energy is converted into mass. This follows Einstein's famous formula, E equals mc squared. It creates heavy particles that didn't even exist before the collision. These new particles only live for a tiny fraction of a second. They quickly decay into lighter particles. But detectors around the collision point record every single spray of debris. By analyzing these fragments, scientists can infer the existence of fundamental particles. This is how they build the standard model of particle physics. Using the LHC, scientists discovered the Higgs boson. This is the God particle responsible for giving atoms mass. Without the LHC, we would never have found it. And CERN still has many questions to answer. What are dark matter and dark energy? Why is there more matter than antimatter? Is there evidence for supersymmetry? In short, the LHC is our best tool for exploring the inner workings of the universe. But this tool has a potential fatal flaw. To many, especially in the scientific community, this is progress. But it also brings some very worrying risks. The biggest risk? The LHC might create a black hole. When this possibility went public, it became global headline news. People reacted in many ways. Some downplayed the risk. They said the machine was perfectly safe. Otherwise, why would scientists dare to start it? Others filed lawsuits. They tried to use the law to stop CERN from activating the LHC. None of them succeeded. Then there was the dark humor. People joked about the impending apocalypse we were all facing together. But these concerns weren't just baseless whining. First, let's clear some things up. Some information back then was total nonsense. For example, CERN is not building a portal to hell inside the LHC. Despite what some people said on Facebook, you can relax. That's been thoroughly fact-checked. However, the black hole scare wasn't so easy to dismiss, because according to scientific theory, it actually is possible. So the question is, if there's a risk of planetary destruction, even a small one, isn't CERN being reckless? Let's talk math and science. What is the real risk of a DIY doomsday black hole? Theoretically, making a black hole is simple, though practice is another story. In the vast universe, black holes are born from collapsing stars, supernovas. The forces involved are insanely powerful. They compress atoms into a single point. Electromagnetic forces fail to hold it back. Even proton pressure, the rule that things can't occupy the same space, is broken. Once you cross that threshold, gravity becomes so strong that mass collapses into a singularity. An event horizon forms around it. Nothing can escape the event horizon. Not even light. Space-time is simply too warped. In nature, we only see this with stars 20 times the mass of our Sun. But the laws of physics don't say you must have that much mass. Black holes can be any size, big or small. You can make one out of any mass as long as you can compress it with enough force. In nature, we don't see that force outside of a supernova. But in the LHC, particles are smashed together with incredible force. Is it enough force? That requires some math. Collision energy in the LHC is measured in tera-electron volts, TeV. 1 TeV is roughly the kinetic energy of a single flying mosquito. Doesn't sound like much, right? But remember, this energy is delivered to a proton, a tiny location, a huge amount of energy packed into a tiny space. When the LHC started, the energy was 7 TeV total. Later, it was upgraded to 13.6 TeV. But even that is nothing compared to CERN's future plans. When the 91-kilometer successor, the Future Circular Collider, FCC, is built, the goal is 100 TeV. Yes, the energy of 100 mosquitoes squeezed into a proton. But actually, even that isn't enough to make a black hole, not even close. In 2010, scientists simulated the energy needed. The answer? 1/3 of the Planck energy. The Planck energy is a threshold. At this point, classical physics breaks down. We have to consider quantum gravity. Since we don't fully understand quantum gravity, what happens beyond that point is a mystery. Regardless, the Planck energy is 15 quadrillion times higher than what the LHC can produce. So, we're safe, right? Wait. If that's true, why did CERN say they could create black holes? The answer lies in the nature of reality. Scientists don't all agree on this, but some believe our universe has more than the 4 dimensions we know. If extra, tiny dimensions are folded up in hidden places, things change. String theorists love this idea. If these extra dimensions exist, which is unproven but possible, it changes the math for the Planck energy. It lowers the threshold significantly. It brings it down to a level the LHC might actually reach. So, if this is true, CERN really could make a black hole. If they did, string theorists would finally have proof they were right. That would be a nice consolation prize while the world ends, wouldn't it? But actually, the string theorists would have plenty of time to enjoy their discovery, because the Earth would survive much longer than you think. First, according to our understanding of physics, such a black hole would vanish instantly. This sounds like a contradiction. Didn't we say nothing can escape a black hole? We used to think so. But in 1974, Stephen Hawking proposed that black holes release radiation due to quantum effects. We haven't directly observed Hawking radiation yet. Its wavelength is roughly the size of the black hole itself. We would need massive detectors. However, small-scale experiments with sonic black holes suggest Hawking was right. According to his theory, all black holes eventually lose all their energy. They lose mass. Usually, this takes a very long time. But the smaller the black hole, the faster it happens. At a microscopic level, a black hole would disappear in a tiny explosion. How tiny? Let's imagine the worst case. All the energy of an LHC collision becomes a micro black hole, then it explodes. E equals mc squared tells us how much energy that is. It's roughly the kinetic energy of a 1 milligram grain of sand moving at 2 meters per second. In other words, a few flying mosquitoes. If that black hole exploded in your hand, you might barely feel it. CERN is actually looking for this. Detecting Hawking radiation would be the discovery of a lifetime. They just haven't seen it yet. But what if we're wrong about Hawking radiation? It's never been directly seen. Some speculate that at a microscopic level, black holes might stabilize instead of evaporating. If a black hole stayed around, would it eat the Earth? Contrary to the movies, a black hole isn't a vacuum cleaner that sucks everything in. Things can't escape the event horizon, but you have to get in first. At a microscopic scale, the forces pushing you away are much stronger than the forces pulling you in. Outside the event horizon, a black hole acts like any other mass. It exerts gravity proportional to its mass. And we are talking about a tiny mass. Gravity is a very weak force, especially compared to electromagnetism. If you aren't being sucked into the coffee cup on your desk, you won't be sucked into a black hole with the mass of 2 protons. Plus, such a black hole would have an electromagnetic charge. Harvard professor Avi Loeb published a paper in 2024 about this. He suggested a black hole that ate a proton would carry a positive charge. It could actually be bound by electrons, just like an atom. It would behave like any other atom, just more compact. This means if CERN made a tiny charged black hole, it would probably just sit on the floor. It would be held up by electromagnetic repulsion, just like your feet are right now. But let's remove the charge. Let's remove Hawking radiation. Let's stick to a 4-dimensional universe. Could a tiny black hole swallow the Earth then? Still, no. Without a charge, the black hole wouldn't be repelled by atoms. It would fall right through the floor. It would pass through the center of the planet and out the other side, completely harmless. True, any atom it hit directly might get trapped in the event horizon. The black hole would gain a tiny bit of mass. Theoretically, it could grow. But in reality, the chance of a tiny black hole hitting another particle is near zero. Think about neutrinos. Trillions pass through your body every second in your entire life. The chance of a single neutrino hitting an atom in your body is about 25%. Atoms are mostly empty space. If the nucleus is a marble in the center of a stadium, the rest is just void. Without electromagnetic interaction, hitting that marble is nearly impossible. Our black hole might get lucky and hit a few atoms in the Earth's core, but it wouldn't gain significant mass for billions of years, not before the Sun turns into a red giant and destroys the Earth anyway. And here is the final nail in the coffin for the doomsday theory: cosmic rays. CERN smashes particles to make black holes, but our planet is bombarded by high-speed particles from space every single day. These particles hit our atmosphere with energies similar to the LHC. If this process could create dangerous black holes, they would have formed millions of years ago. So, you see, if reality has extra dimensions, and if Hawking radiation doesn't exist, and if CERN makes a neutral black hole, and if that black hole gets incredibly lucky, then yes, maybe it could hollow out our core and collapse the Earth. But it's probably never going to happen. In history, scientists have taken risks that caused real harm. That's why we have ethics and safety protocols. But CERN and the LHC are not that. The probability is too low. The danger is practically non-existent. We are safe. Unless they actually do open a portal to hell, maybe we should check that theory next, just to be sure. But seriously, the story of the LHC tells us something deeper. Humanity's quest for the unknown is always shadowed by fear. From the first fire to the first split atom, people have predicted the end of the world. But it is this courage to push boundaries that moved us from caves to the stars. The black hole didn't eat the Earth. Instead, we found the Higgs boson. We confirmed why matter has mass. It was a giant leap for human knowledge. Next, scientists want to solve dark matter. They want to know why the universe is accelerating. They want a theory of everything. Maybe one day, we will look back and laugh at the time we thought a particle collider would swallow the world. Until then, we shouldn't stop exploring. We should just move forward with awe and caution. One last question for you. If a scientist confirmed an experiment had a 0.1% chance of destroying Earth, but a 100% chance of revealing the secret to eternal life, should we do it? Let me know in the comments. Let's talk about it.